we go. 51, 52. All right, welcome to Quantum Mechanics 1 Interpretations, where I will review some of the major ways of interpreting quantum mechanics. My name is Robert Nemeroff. This is Michigan Tech. This is Physics X, Extraordinary Concepts in Physics, where we try to explain some of the coolest concepts in physics. So this is a course being taught at Michigan Tech, but available over the internet, and there's no textbook, it's only Wikipedia links. So there are many interpretations, actually, of quantum mechanics. Quantum mechanics is so strange, I would say it's not fully understood. No one, as Feynman has once said, no one really understands quantum mechanics. And so people try to come up with ways of understanding the mathematics. The mathematics is actually, in some levels, quite predictive, particularly in the non-relativistic regime. In many regimes, quantum mechanics can give you the best predictions that can be made. Particles will end up here. Classical mechanics doesn't apply, but there are some very strange circumstances that really gets into what is happening. And so it's popular to debate this. It's really strange, and to think that our universe is so strange that we can't even interpret some of the basic relations. So the last couple lectures I talked about the uncertainty principle, and actually I'm going to get back to that most probably in a future lecture. But now I'm going to go after not only the uncertainty principle, but quantum mechanics in general, the interpretations of what quantum mechanics is. And so I'll be reviewing 4 of them: the Copenhagen, the many worlds, the ensemble, and the hidden variables, as best I can, as best I understand them. So let's get to the first one, the Copenhagen interpretation. I think it's named after Niels Bohr, a famous physicist, and his group of people who would interpret quantum mechanical results. So Einstein didn't like the whole probabilistic aspect of it. So he was against generally he thought quantum mechanics was an incomplete theory, and that it appeared probabilistic because we just didn't know enough about it. It's like not knowing anything about the weather, so saying, well, the weather tomorrow may be sunny or not sunny, so you just don't know. But if you know enough, you can get better and better at predicting it. So he thought quantum mechanics is a little bit like that. We just don't know what's going on, so we can't predict what's going on. But the Copenhagen interpretation says, well, we pretty much know everything that's going on, and you can't do better. There is a fundamental uncertainty in the universe that you can never beat. And there's things like the Schrödinger equation that describe the probability wave of something that moves around. Actually, it's the square of that wave. So a particle doesn't just move, it has a probability wave that moves an amplitude. And so the wave function collapse is something that is fundamental to the Copenhagen interpretation and is one of the things that's most debated. So back to my single source, my single slit experiment. So you have a photon moving toward a single slit. So one might consider that this photon could have been anywhere. It could have been here, 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 and here. But when it goes through the single slit, in a sense, its wave function, which could have been probably anywhere, then must be confined to where the slit is. It's essentially being measured at that slit. Later, when it goes to hit the screen, one can say, well, it could have hit anywhere on that screen, or the probability distribution of where it could hit on the screen, but then it happened to hit here. At that point, the Copenhagen interpretation would say its wave function collapsed. It no longer was what it was. It's now suddenly, when it hits, then it changes from a probability distribution to here it was, or here's where it was measured. So it is the collapsing nature that many people find frustrating, that suddenly things change like that. So there are other ways of interpreting things, and this one's even weirder. And I think it was considered really weird, particularly when it was suggested and didn't hold much favor, but actually it's really gaining in popularity now. The many worlds interpretation says that every time there's a quantum measurement, each outcome is realized in a different universe. So let's say your photon goes through a single slit, and then there's different places that it could end up. It could end up here, it could end up here, it could end up here, it could end up here. These are the pixels, let's say, on your digital camera that can measure the photon. when the photon measures here, that's great. A universe then goes off and is created, and there's a universe where the particle hit here. And if the particle, when the particle hits here, that's a completely separate universe. Each one is a different world line, sort of. That's probably a bad way of saying it. But each of these universes, every time a quantum decision is made, a universe is created. And those universes together create a metaverse. So there is no wave function collapse. It's just here. It was here. It wasn't. It had a probability before, so the mathematical formalism is the same. But then a universe sprung off when this quantum decision was made. So the observer here doesn't really trigger the wave function collapse. So it's different than the Copenhagen interpretation, although people sometimes struggle to come up with why it's mathematically different. It's because the mathematics is essentially being interpreted as many times the same. The terminology that is used instead of wave function collapse is that the wave function becomes increasingly coherent or incoherent, decoheres. Its decoherence occurs by information leaking from the quantum system out from it. And each time that happens, another universe is created. So the many worlds or many universes interpretation. Okay. Here's another one, one I happen to like. Don't apply quantum mechanics formalism to individual particles. Some people consider that quantum mechanics only refers to particle ensembles. So if you can create, if you tried to have many, here's a photon moving toward a slit, and here's a wall. So quantum mechanics doesn't really say what happens to one particle. It can only say what happens to many particles that are created in as close to exactly the same way as possible. Then when you have lots of these, then you can build up a probability distribution where more of them hit here and some of them hit there. So trying to attribute it to a single particle is actually a mistake. Einstein at some times supported this much more than the Copenhagen interpretation. He said, okay, maybe I can see this ensemble interpretation better. However, some ways of interpreting the ensemble interpretation attribute the probability to a classical ignorance and not quantum mechanical indeterminacy. Some ways of interpreting the ensemble interpretation, so you have to interpret interpretations. So this is one of the major ways of interpreting quantum mechanics. The last one is something that actually has been discussed in detail. So this is the one that Einstein thought was operating the most when he was trying to shoot down quantum mechanics as an incomplete theory. Einstein thought it was an incomplete theory because he thought there were essentially hidden variables. Now there are other people who picked this up. Bohm, for instance, BOHM, worked with this in detail. So there's untracked complexities like the weather is. For the weather is very complex. If you don't look at if you don't know what's happening around you, you just don't know what the weather is going to be later today or tomorrow. So quantum mechanics is the same. We don't know much about what's going on. There are things happening in the universe. There are other variables they're going on that we're not tracking. So when you track the photon, you only track its position x. Here, delta x, it has to be between here and here. It's momentum p. There's other things that could become important. There might be, I don't know, some strange variables that are involved with the universe somehow. I can't even guess what they are. Like if the photon might have internal degrees of freedom, it might be a little rotating ball. And in this ball, there are little spikes that stick out in certain ways. And these spikes hit little things on the side or interact with the air or the ether in some ways as to cause it. And we don't see the little spikes. They're too small. We don't understand the air or the ether that's there because we can't see it. And if we could, then we could predict exactly where that photon would go. So this is the origin of Einstein's famous phrase, God does not play dice. And Bell came across, and later, after Einstein left, died, unfortunately, he didn't just leave the room, that Bell realized that hidden variable makes very different statistical predictions than other interpretations, which could be the classical other interpretation is the Copenhagen interpretation. Classical is the wrong word. The most commonly used interpretation is the Copenhagen interpretation. So Bell actually tested this, and we'll be looking at Bell's inequality and in the future in many lectures in detail. But I will say, though, that it is found that this is not right. That it's not that we don't know. It's not that photons are made of little balls with little strings hanging off them and little things that make them so complex that we don't understand it. There is a fundamental uncertainty in statistical way that the universe works. And it's not because we don't know about the universe. There is no way that we can think of defeating the uncertainty principle and predicting things. It's not because we don't know. It's because it's a fundamental part of the universe. And that a lot of experiments in the past 30 years have gone into that in a lot of detail. And so far, we can't beat the uncertainty principle. So it could be that any of the other interpretations of quantum mechanics might be best. The many worlds, the Copenhagen, the ensemble might turn out to be best, or they might turn out to be there's no way of discerning between them mathematically. But the hidden variable one, where we just don't understand, that can be attacked and has been essentially, so far as we understand, defeated. That's not the way to think of the uncertainty principle. It's not that we don't know. It's that it's unknowable. And with that, I will close. And in a little bit, we'll talk about Schrodinger's cat, which gets into some of these interpretations in more details. That will be in a lecture or two, but it won't be this one. So until then, I'll see you next time.